Boom. Wait, is this one summative? 3.4 second derivative test. Time to take a summative. Ha! JK, obviously. So today we're learning to use the second derivative to determine extrema. We'll be successful when we can successfully apply the second derivative test. So we already did the first derivative test, and that was determining if a function's increasing or decreasing by the sign of the derivative. If the sign of the derivative is positive, it's increasing. If the sign of the derivative is negative, it's decreasing. So we had that. And then we talked about if you have a critical point, you can find out if it's extrema by seeing if it changes sign. And if it changes sign, well, it depends. Does it go from positive to negative? Or does it go from negative to positive? So it makes a difference because it's either a maximum or a minimum. So today we're going to look at what the second derivative test is. And also some other things. All right. So this would have been a thing that we would have done at your teams, individually, working on stuff. But we're just going to do it together. So I'm going to keep using this graph because there's a lot of great stuff we can pull from it. So there's a bunch of things that I'd like to try to identify. I want to try to identify where the graph is concave up, intervals where the graph is concave down, the concavity at local extrema, points where the concavity changes, and if we have time, and we will briefly, determine the approximate concavity at global extrema. All right. So concave up, just quickly, concave up and concave down. If you don't remember this, concave up kind of looks like a cup. You should see things that generally look like this. Concave down is an upside down cup. I didn't have something better for concave down. If you think of something better for concave down, let me know. But concave up is like a cup ready to be filled. Concave down is a cup that's empty and is just waiting to be used. So looking at this graph, we can approximate where things are concave up and concave down. So let's do that. So I am sharing. Sweet. It's approximately concave up on the interval 0 to 5. And again, that's interval notation. So I'm just saying on this open interval 0 to 5 or 0 to 0.5. And then the open interval 1.2 to 1.7. So again, just kind of looking at the graph for those. This piece right here, it looks like it's like an open cup ready to get some coffee poured into that. And over here, same thing. Now, why'd I pick 0.5 and not maybe further on? I don't know. It just looked like maybe that was the point that started this upside down cup that was just waiting to be filled with coffee. I don't know. Maybe you can make an argument that at some point later on, but that's part of the hard part about doing this with a graph is that it's difficult to know exactly where that spot is. That's something we're going to hit at later. But with a graph, we can approximate. So it's, again, approximately from 0 to 0.5, looking at that range, or that interval. And then from 1.2 to about, I said 1.7, because then it looked like it started turning into an upside down cup. All right. That's concavity. Again, concavity, another way to think about it is how is the slope changing? Is the slope getting more positive, more negative? If it's getting more positive, it's concave up. If it's getting more negative, it's concave down. So that's also something to be aware of. So I just want to point that out. So again, the slope's getting more positive here. Here, the slope is negative, but it's getting less negative and more positive. So it's still concave up. Let's look at the intervals where it's concave down. Again, we're approximating that right now because we just have a graph and it's hard to say it exactly here, which we'll do in a little bit. Like concave down, well, it looks like 0.5 is a place where it kind of changes because now it kind of looks like, all right, well, the slope's getting more negative now or less positive, more negative. And then probably right about over here to the end. The slope's getting more and more negative throughout that process. So something else I want to think about, just because I'm curious, is what's the concavity at the local extrema? Now we had 3 local extrema here. We had 2 maxima and 1 minimum. It's concave down here, right? At the maximum, it's a cup upside down, just waiting to be filled with coffee. The minimum, it's a cup ready to be filled with coffee. And then at this maximum, again, it's a cup just waiting to be turned around to be filled with coffee. So that's interesting. That's something to be thinking about. And we'll come back and talk about that more later. Points where the concavity changes. You could argue for a couple more than what I included, but I said there was 2 points. Now I labeled these points as XY coordinates. I probably should have just said like X equals 0.5 and X equals 1.7. But that's how I decided to do it at that point in time, pun intended. So at 5, 5 or 0.5, 5, it looks like that's where it goes from open cup to or cup with coffee to cup without. Because it can't be upside down unless you have a really nice mug and keep the coffee in. And even then, it's not going to look like a regular coffee cup that way. And then again at 1.7, X equals 1.7, Y equals 2.5, looks like another point where the concavity changes, where it goes from that open cup to that down cup. This blue one, approximate concavity at a global extrema. Well, here's a global minimum, here's a global minimum, here's a global max. It really depends on the rest of the graph. It doesn't have to be anything in particular. Like right here, it's concave up. Here, it's concave down. Here, it's concave down. So it doesn't really matter if it's a global extreme or not. It matters more about if it's local. All right. So we just looked at concavity on a graph. What I want to do now is remind you that on the graph, we're just approximating where the concavity is. We didn't exactly determine it. Now, and that's something that we kind of did in pre-calc because we just approximated where concavity was. But we have more tools under our belt now, and we can exactly determine what the concavity is and where the concavity is. But we need an equation to do that. So I have an equation that we're going to look at. C of x equals x to the 4th plus, whatever, it's right there. We are going to try to do this. We're going to identify intervals where the graph is concave up, intervals where the graph is concave down, the concavity at local extrema, and the points where concavity changes. We're going to try to do that exactly for this. To do that, I'm going to give you some more information because we could graph it and approximate it, but I want exact values. And this is one in particular that we can't just approximate. Like all the points are kind of off a little bit. I intentionally did that so that it motivated us like why we had to do the thing. So let's take a look. Here's something that I'd like you to make a note of because this is important and we're going to keep using this over and over. So you do a first f prime is you've done the derivative once to the original function. F double prime is the second derivative, means you've done the derivative to the original function twice, or AKA you've done the derivative to the derivative. So like if I have x to the 3rd, the first derivative is 3x squared. The second derivative would be 6x. The second derivative, so the first derivative tells us whether things are increasing, decreasing, maxima, minima, whatever, all those things, those critical points. And it also helps us get critical points. Second derivative helps us determine concavity. Is the slope increasing? Is the slope decreasing? Is the cup open or closed? So that's what the second derivative is going to help us with. So as you can see, when it's positive, when the second derivative is positive, f of x is concave up. When This second derivative is positive, f of x is concave up. When second derivative is negative, then f of x is concave down. When it's equal to 0 or does not exist, it could be a point of inflection. So we don't call it a critical point for the second derivative. It's just a possible point of inflection. It's only a point of inflection if the concavity changes sign. And we don't have a different name for if it goes from positive to negative or negative to positive. It's just, does it change sign? Yes, no. And it's a point of inflection. So that's what the second derivative is going to help us with again. It helps us determine the concavity and points of inflection. This is not the second derivative test. We're going to get to the second derivative test, but this is clearly not the second derivative test, especially if you understand like the reference in this meme. So we are still going to just play around with the second derivative and see how this works. All right. So we're going to focus on these three first. In order to do all this, we need to figure out what the second derivative of c of x is. So there's the first derivative, just a bunch of power rule, noise. Oh, yep, I did that right. I got really confused for a moment. I'm like, this is 24x. Why is it 30? And then I realized what I did. So this is correct. It's fine. We're good. So now I'm going to take the derivative of c prime, which would be c double prime. And I get 12x squared plus 24x minus 34. Now what I want to do, now that I have the second derivative, let's see where it's 0. Now, the fun part, and fun's probably relative here, is we're going to have to use quadratic formula on that because there is not, it doesn't factor nicely. So we're going to have to use quadratic formula. So here it is. There's all the work to show the quadratic formula. To 3 decimal places, it gives me 2 x values, negative 2.958 and positive 0.958. So now what I'm going to do is I'm going to make a sign chart for the second derivative. There's my number line. And remember, whenever you make a sign chart, always label it. Is it f, f prime, f double prime? I'm labeling this one as f double prime because I want to know what it is. Now, these are possible points of inflection. So what I'm going to do is put a spot for each of them, label them, and mention that f double prime is 0 at both those spots. Okay? Now what I need to do is I need to test in the second derivative a number in each of those intervals to see whether f double prime is positive or negative. And I should have said c double prime as I'm reflecting on how I set this up. And totally spaced on that. Apologies. So when I say f double prime, realize that should be c double prime. Do I have time? I might fix that right now. Yep. I was like, come on, be a text box. Come on, be a text box. And it was. There you go. All right. So now we need to test a point on each of these intervals in c double prime. So I don't know, over here, maybe 1,000 or negative 1,000. Really positive, negative, but not as much as this is positive. So that interval is going to be positive. This interval, hey, 0's in that interval. Let's plug that in. When I plug in 0, I get negative. Let's plug in, like, I don't know, 50,000 for this one, just because it's fun. That's a fun number. And when you do that, you get positive. Sweet. All right. So here's what we're going to do from this. We have all the information we need on this sign chart of f double prime. Just open up chat just in case I missed something. So now we can determine a bunch of things. So let's see what we have to say. Again, this is not justifiable for work, but it's scratch work to help us make our justifiable work. So I can say f is concave up on those two indicated intervals because f double prime is positive on those intervals. That's how I expect you to say something's concave up, is you tell me literally that sentence. All right, where is the graph concave down? Right there on that interval. I also realized that I probably should go change the color on these because it would make more sense if this was green and not red, but oops, that might fix that later. But f is concave down on that middle interval because f double prime is negative on that interval. Now coming back to those two numbers that made c double prime 0. Looking at those, the concavity, does it change sign at those points? Does it change from positive to negative or negative to positive? It sure looks that way. So we can finally say x equals negative 2.958 and x equals positive 0.958 are points of inflection because f double prime changes sign at those points. Boom. There, that's that. All right, so we've hit all three of these questions. Money. There were two other questions. The blue one wasn't super important, but I want to look at this. This is the graph of c of x. I want to see what's the concavity at the local extrema. Well, here's the sign chart for f double prime, and we can kind of see how it lines up with c of x. And again, this should be... I don't think I had anything else there. There we go. So there we are. There's c double prime, there's c. We can kind of see how that concavity matches up. There's the open cup until about almost negative 0.3. Then it starts changing to a closed cup. And then about just before 1, it starts changing from that closed cup to that open cup. And we can see that from there. But again, looking at the concavity of the local extrema, it's positive at this minimum, negative at this maximum, and positive at this minimum. That's cool. Like, we can confirm some of those things, but we can say the concavity at these local extrema, and we just identified it here by overlaying our number line on top of the graph of c of x. This lesson's entitled The Second Derivative Test. What the heck is the second derivative test? Because we've gone through the whole lesson, basically, and we haven't even mentioned the second derivative test other than me joking with you about the fact that whenever I say test, the first question I always get is it summative? Sorry. It just always makes me laugh every time someone says that. So what is the second derivative test? Because that's kind of a thing. Like, this lesson's literally titled that. Technically, it's second derivative test and concavity. So we spent most of the time on concavity. But what's second derivative test? I could just define it some other ways. Wolfram Alpha gave me a nice little definition. So if f of x is a function that's twice differentiable, meaning that you can take the derivative of the function and its derivative at a stationary point. Stationary point just means f prime is 0. If the concavity is positive, that critical point is a minimum. If the second derivative is negative, then a critical point's a maximum. That's what the second derivative test is. Most of the time, the second derivative test isn't super useful for most of the things we're doing. But it is a shortcut way to be able to explain why something's a min or a max. Like, if you don't want to say, well, it changes from positive to negative here, you can say this critical point is a minimum because it has positive concavity at that spot. And here, again, here's the graph of c of x again. Here are the coordinates of the mins, the min, the max, and the min. So you can see the x values for each of those. Here's each of those x values and then evaluated in the second derivative. Well, it's a minimum and it was positive, right? Minimum, positive. That makes sense. Maximum, negative. That makes sense. Max or minimum, positive, minimum. Boom. All the things kind of fit together there. That's the second derivative test. Oh, that's right. I forgot I animated those. Look at all that. In all of its glory. So one last thing that I wanted to talk with you about is just kind of, now that we're not just using F and not just F prime, but F double prime, I just want to remind you about what each of the things we can use to represent. What do we use them each for? F, we use to find a location. Like, what are the coordinates of something? F prime is the slope of F. We use it to determine if F is increasing, decreasing, and has extrema. F double prime is the slope of F prime. And we also use it to determine the concavity of F and if it has any points of inflection, POIs. That's it. Here's your practice. Oh, while I'm thinking about it, let me add one more box in. There's some post credits that you might want to check out. Again, I'd recommend checking out post credits pretty much anytime they exist. Post credits basically just have extra work and stuff that may or may not fit in to what we're doing. We are doing another MCQ Royale, if I can spell Royale. So we're going to be using Unit 2 progress. We're going to use Unit 2 MCQ Part A. Oh, Part A. So what you should do to prepare for that on Friday is make sure that you take some time to go to AP Classroom, start working on as much of that Unit 2 multiple choice progress check Part A as you can. On the last one, you all got 5 out of 9 correct. But again, almost none of you spend time working on it ahead, like before we started working on it. So considering we got 5 out of 9 with almost no one working on it ahead of time isn't terrible, but we can still do better than that. I believe in you, and I know you can do better than that. So spend some time going through that. I wouldn't submit it yet. I would submit it after you do the MCQ Royale, because so that you can see some answers and stuff from there. If you're not going to be here Friday, just let me know. But make sure you spend some time on that the multiple choice, that progress check, Unit 2 Part A. It just got assigned, I think, last night. So that's what I have for you today, folks. Again, make sure that if you have questions, so send me a message in Discord, post in the Discord channel. Mr. Weimer or myself will respond to you, or someone else will, like another classmate, or send me a message, email me, come to the drop-in, the Comedy and Math Support Hour, Monday, Tuesday, Thursday, Friday from 12:30 to 1:30. I mean, if you want to come tomorrow and work on a couple of these, we totally could. But again, like, just let me know, talk to me. The more you talk to me, the more I can help you out and stuff, and kind of go from there. So on that note, have a wonderful day, folks. We'll talk to you later.